Very good. Thank you. Thank you so much, everybody. And welcome, everybody. Thank you for joining to our December Superfund Research Columbia program at Columbia University for our seminar. And I am going to ask Ben, would you like to introduce our first speaker today? And then for the second round, I'll introduce our second speaker.
Sure. It's my pleasure today to introduce Mindy Erickson from the USGS and I guess also at the University of Minnesota. Mindy has dedicated much of her professional career, or most of her professional career, to understanding the distribution of environmental contaminants across the Northern Plains region that we're hoping to work at in the future, and many of us who are already working at it as well. Mindy lives in Minneapolis, or sorry, works in Minneapolis, at least I should say, and has worked in, and actually originally comes to us, or to that subject, through working with the public health effects of arsenic. And it's a real pleasure to be able to work with her and gain some expertise from her as she's hopefully becomes a part of our future work as well. So I'll keep it simple, and with that I will let Mindy tell us a little bit more about arsenic and other contaminants across the Northern Plains here. Okay.
Great, thank you for that introduction, Ben. I'm actually going to talk pretty much exclusively about arsenic today. Little touches on other things that are related to arsenic, but the arsenic will be the focus. And just as a small additional introduction, my first work with arsenic was on an 18-month project with our Minnesota State Department of Health. I had been working as an environmental consultant and was looking to make a change, and found this short-term project. I thought, hey, that'll help me, get a little time, figure out what I want to do next. This was back in 1998, and I had zero idea at that point that 18-month project was going to change the complete rest of my career. So since 1998, I have been working on issues related to arsenic and groundwater in Minnesota and the upper Midwest and across the glacial aquifer system that spans coast to coast in the northern US. My talk today is going to focus on the upper Midwest and Minnesota drinking water aquifers. And with that, I'm going to try to again successfully share my screen, and we can get started. All right, do we have slides now?
Indeed we do.
Yay, great. So again, we're going to start with a focus on the upper Midwest, and then focus in a little bit more in detail on Minnesota specifically. I'm going to speak today first with presenting a little bit of a glacial geology primer. Ben told me that the audience for this seminar series is fairly broad, and so I wanted to make sure that we all have at least a basic understanding of what glacial aquifers, what I mean when I talk about a glacial aquifer. Then a little background about arsenic here in our setting and our particular study motivation and design in our geologic and hydrogeologic setting. And then talk about results from a few different angles. And there should be plenty of time for questions and discussions after the presentation is concluded. So with that, let's launch into a little bit about glacial geology in general. So Minnesota is situated in the central part of the northern US. And by glacial, we mean materials that were deposited related to the glaciation we specifically are talking about the northern US and Canada. And the period that we're talking about is from about 2.5 million years ago to about 12,000 or so years ago. And this is generally called the Quaternary or the Pleistocene, sort of depending on the setting and the audience that you're talking to, though either of those terms can be used. But that's the period of time we're talking about. And specifically here, we're talking about Minnesota, that had glacial ice advances and material advances from both of these major domes in the continental US, the Keewatin Dome that came from the north-northwest and the Labrador Dome from the north-northeast. And this becomes important when we talk about the provenance and the nature of the sediment that was deposited by the glaciers that came from these two different directions. So another term you'll hear used is the term till. And till is the name of a material that is unsorted. So it can have grain sizes from clays to boulders. And this photograph is just an illustration of the general concept of till, where you have these larger, coarser fractions embedded in silts, sands, clays, etc. So that's a general description and picture of what till looks like. The other thing that's important about till in general is that it's thought to be a more impervious or a slower groundwater, or slower water flow through till because it is bound in this finer grained matrix. So in amongst the till in this glacial setting, we have what are called aquifers, which are the coarse materials from which we generally draw water from wells, interbedded with aquatards or confining materials, generally a till layer that then can surround the aquifer materials. And within the glacial setting, there can be fairly complex stacks and settings of these aquifers and aquatards interspersed, and then all of that is above the bedrock aquifers that then underlie this glacial material. You'll sometimes hear glacial material also called overburden. I don't tend to use that term because I don't think it's very descriptive, but if you hear that term overburden, that is often used to describe or to name glacial materials that overlie bedrock. So then moving straight into the arsenic in the drinking water aquifers here in the upper Midwest. I think all of us are aware that arsenic is a trace element that is a contaminant in many parts of the world, not just in glacial aquifers in the upper Midwest. And that the primary source of arsenic in drinking water worldwide is geologic sourced, not from human-caused sources. Many different types of health risks are associated with arsenic exposure that's resulted in the Environmental Protection Agency setting a drinking water standard for public water systems, and the World Health Organization setting the same standard at 10 micrograms per liter. As with any carcinogen, EPA has a goal, the MCLG, of no arsenic in drinking water. Both New Hampshire and New Jersey have set statewide MCLs or drinking water standards of 5 micrograms per liter. Here in Minnesota, the 10 microgram per liter standard is what's in place. But because of the widespread occurrence of high concentration arsenic, a new rule was put into place in 2008 that every new potable well has to be tested for arsenic before it can be put into service. And the state health department recently changed its advice regarding treatment of arsenic in domestic well water. The recommendation now is for consideration of installing a treatment system for drinking water if there's detectable arsenic versus strictly arsenic above the drinking water standard of 10. So that's I thought that was a really important shift in messaging. As you can see from the map of arsenic measurements in Minnesota, it's not evenly distributed at high concentration, that there are certain areas that have a higher percentage of wells with high concentration. And many of these areas that have no measurements can be either places where there aren't very many people living, which is the case in the northern part of the state. This is the Boundary Waters Canoe area and a lot of forest and other undeveloped land. Or it can be non-detectable arsenic. The non-detects are not shown on this map because it just makes the map too difficult to see. This southeastern part of the state is one of those areas where there are a lot of people living and there are a lot of wells that have been tested, but it's not very frequent to find detectable or high concentration arsenic. So given that the well testing rule went into effect fairly recently, there was some pushback, as you may imagine from your own experiences, regarding implementing this rule change. And getting the rule change made did require some compromises with regard to specificity on the collection of that sample from the new well. So the well code does not specify the location from which the sample is collected. It doesn't specify the timing, except that it has to be within 30 days or before the water is put into potable use. So, it's not super specific. And the samples aren't field filtered. So here, just in Minnesota, there are 180 licensed well drillers and 12 laboratories that are certified to analyze for arsenic. So amongst all of these different considerations, there was some question about how good are these arsenic results? And, we can all wave our hands about it's good enough, or it's not good in this way, or it is good in this way. But we really wanted to try and quantify what it was we weren't and were getting from these new well results. Given at the time the study was done, there were about 40,000 results. There are now about 60,000 results in place. So, there's a lot of investment, a lot of money being spent on the testing. It's good to know what those results may or may not actually mean. And the questions arise because well drilling does disturb the equilibrium of the aquifer and by extension, the geochemical conditions. Air and aerated water are introduced during the drilling process. The sediment gets mixed up. A big dose of chlorine is introduced for disinfection. And then during well development, and then finally when that well is put into use, the heads change within that aquifer just because of this new pumping that's happening. And so there were two major questions that our study wanted to address. The first was whether or not sampling methods, choices made about how and when to collect those samples, introduce bias into the results. So that was one question related to sampling. The other question was whether or not there are temporal changes in arsenic concentration over time after a well is put into the future. And so those are the two main points that I'm going to discuss and the results of that. But first, let's take a step back and talk about the study design that we used to try and get at those two questions, answers to those two questions. So we designed a study that sampled about 250 domestic wells over the course of a year at 3 specified periods. The first we call round 1, and this conforms to the regulatory requirement for water well sampling and analysis. So the sample was collected within a month, And our sampling crew tried to replicate the method with which an individual driller collected the sample. So if the driller would collect the sample on drilling day after well development, that's when our field crew would collect the sample. And this, as you can imagine, can result in some samples that have significant sediment in them because the well is new and the water is coming up in with a high-speed pump, etc. That's the way that some drillers collect those regulatory samples. Other drillers have a different process. They put in the well and then they come back sometime before the well is put into service. They install a pump or something like that, and so then they collect that regulatory sample through household plumbing or through some other sort of plumbing system. And so both of those sample collection methods are acceptable for the regulatory purpose, but they're pretty different types of samples with regard to geochemistry and what you might expect to see in that water sample. So we collected samples that replicated the driller sample, whatever that was, however they did that. But then alongside that, we also did filtration in the field to get an aqueous arsenic sample, eliminating the results that can muddy understanding from any sediment that might be in that sample. And then we also collected some other redox sensitive constituents like iron, manganese, and nitrate, and then did the general suite of field parameters, looking at measured EH, a measure of the redox condition, dissolved oxygen, pH, and conductivity and temperature. So that was the first sample, again, collected within 1 month of the well being drilled to conform with the regulatory environment. And then we came back 3 to 6 months later and about 12 months later and did just a replication of these samples that are listed here under the study samples, the total and aqueous arsenic, these other redox sensitive constituents, and the field parameters. And all of these samples were collected from plumbing. There's no drill rig there anymore, obviously. So that's the study design. That's what we did. And then looked at these samples, initial sample, 3 to 6 month sample, 12 plus month sample, termed round 1, round 2, and round 3. In terms of our geologic setting, we targeted 2 areas that were known to have a higher prevalence of high arsenic than the statewide average. And then we also looked at this northeast region, and this is what called the northwest region and the central region. And then we also collected samples in the northeast region of Minnesota. This is an area that we really didn't know very much about before with regard to arsenic, but when the water well rule went into place, what the state health department noticed was that the number of samples that exceeded 10 micrograms per liter were about the same as the statewide average. But when these samples were above 10, they were far above 10. These were samples that were closer to 100 micrograms per liter, not flirting with that 10 microgram per liter. And so the health department was very interested in trying to get a handle on what was happening here in the northeast region. And so we picked 50 wells in the northeast region, 100 wells each in the northwest and central region. The northeast region is, this is Lake Superior, is over here just off and not shown. And so this is called the North Shore of Lake Superior here in Minnesota. And in general, domestic wells and public supply wells will often tap into the bedrock aquifer that underlies the glacial material. The glacial deposits that exist here in the northeastern part of the state generally were from that northeastern provenance ice. And so this glacial material tends to be coarser and it tends to be a much less much less impermeable, so a more permeable till. And you can see here, as illustrated on this cross section, that wells tap both the bedrock aquifer and the glacial aquifers here in this area of northeastern Minnesota. This material also tends to be more crystalline versus the material that was deposited from the northwest provenance. The northwest provenance that came over shales and carbonates. And so the material that makes up the glacial sediment in the northwest and central regions tends to have a much higher shale content, higher carbonate content. And in the central region here, as depicted by the cross section, the areas of till and the aquifers tend to be more extensive and more continuous, versus this northwest region. The till and aquifers tend to be much more discontinuous, much more isolated from one another, because of the number of glacial advances and retreats that happened in this up ice part of the state. So in summary, the material that we see in the aquifers in the northwest and central region tend to be similar. It's just more extensive in terms of the way the material lays in layers in the central region versus the northwest region. The northeast region has very different material laid down from glaciers that came from a different direction. And one of the things that we found as part of a related but separate study is that arsenic is ubiquitous in the sediment in both the northwest provenance materials and the northeast provenance materials associated with both iron oxides and iron sulfides. And the importance of this will be highlighted a little bit later in the talk, but I just wanted to introduce that idea here in the background material. In terms of why it's important where the arsenic resides, whether it resides in oxides, which are illustrated by this rust over here on the right-hand side, or sulfides, illustrated by this beautiful example of pyrite here on the left, is that they're stable in very different geochemical environments. So in oxidizing conditions, the oxides are stable, and in reduced conditions, the sulfides are stable. So we have arsenic associated with different iron minerals at two different ends of the redox spectrum. So we can have arsenic mobilized from sulfides in oxidizing conditions. We can have arsenic mobilized from oxides in reducing conditions. So the arsenic is traveling with the iron and the sulfur under these different redox conditions. And so redox plays a really important role in arsenic mobilization or arsenic sequestration. All right, and before I launch into results, does anyone have any questions about the background material? All right, we'll just move on, hearing nothing. I'm going to present the results in three different chunks. First, talking about the well sampling methods, then talking about the temporal changes, and then I'm going to talk about a surprise, give a little presentation of some hot off the presses results that were just finalized and are in press right now. So first, just a general overview of what we found. In the Northeast region, as I said, we had high arsenic, that is above 10 micrograms per liter at about the same rate as is true statewide. Statewide, it's about 11%. The Northeast region was 10% of samples higher than 10 micrograms per liter. In both the Central and the Northeast region, we had much higher than the statewide average prevalence of high arsenic concentration. This was right in line with what we expected to find. Overall in the study, about 80% of the samples had detectable arsenic, with the detection level being nominally 2 micrograms per liter, which is what's required for a laboratory to be certified for arsenic for the Minnesota regulatory purposes. In terms of looking at results of how samples were handled and when they were collected, we did a comparison of the driller collected samples, the initial, so this is an unfiltered sample, the aqueous initial samples, and the 3 to 6 month samples, comparing them to the 12-month aqueous sample, and whether or not that sample location had a change in the reported concentration that flipped above and below the 10 microgram per liter drinking water standard. And as you can see, these unfiltered driller samples had a much higher prevalence of swapping between categories than did the filtered samples that were collected initially. And the samples that were collected 3 to 6 months later had an even smaller proportion that flipped between these two categories. And at the time we did this analysis, the recommendations from the health department were still based on that 10 microgram per liter standard. And so that's why we're using that 10 microgram per liter above or below as sort of a bright line for looking at these different types of sample handling techniques. And then another finding that we found was that concentrations were about equally likely to increase or decrease over time. And one of the main drivers for looking at the results this way, especially with the focus on samples that could increase in concentration, is that there was the anecdotal message out there from drillers to customers: don't worry, if your sample is high to begin with, it will go down over time. And so the health department was very uncomfortable with this anecdotal message being out there, but they didn't have any data or any information to try and refute that or change that messaging based on knowledge and science. And so that was one of the reasons that we looked at the data in this way, in terms of increases versus decreases and the magnitude of the increases versus decreases. So now they have the information that says, no, they're about equally likely to increase or decrease. And when it increases, it can increase a lot. So please stop passing on that message to your customers, drillers. So that was an important piece of information for them to have. So the summary of the sampling methods paper is that filtering samples, collecting the samples from plumbing instead of from the drill rig, even if not filtered from plumbing, and collecting samples a little bit later reduces the variability of that sample compared with a later sample. And these results were published in 2018 in the journal Groundwater, if you're interested in more information and more details about the study design and the findings. So moving on to the arsenic geochemistry and the temporal changes in arsenic over time, we looked at the results in the 3 different regions separately. Again, this Northeast region is our bedrock region. The Northwest and the Central region are both glacial well regions. And what we found was in the 2 glacial regions, there was a systematic increase in arsenic concentration over time in both of these regions, and no statistically significant concentration change in the bedrock region. In terms of geochemical changes over time in the Northeast, the major change that we had was dissolved oxygen went down and pH went down. In both the Northeast and Central regions, we had some increases in metal concentrations In the Northwest, no substantive changes in DO or redox. The ORP is looking at EH, measured EH or redox condition, and no change in pH. And in the central region, we had the biggest quantifiable changes over time, with increases in all of our metals, decreases in our redox measures, and an increase in pH. So these results really do demonstrate very clearly that the well installation does induce this disequilibrium, creating the disturbing the geochemical equilibrium, and it does take some time. We only ran the study for about a year, so we only have information out to a year, but for at least the course of the year, there is this geochemical disequilibrium.
Mindy?
Yes.
Can you go back to the plot? It seemed to me that most samples didn't change, that it's just a small subset of samples that changed.
It's about 25% overall. This is the summary, and it was about 25% of the samples that had an increase in both of these regions. And all of the data are available for different kinds of slicing and dicing that anyone would like to do as well. If anyone's interested in the data, it's available online associated with the paper. And a lot more about the methods and all that too. All right, and focusing in a little bit more on measures of redox, we took a look at similarities and differences in how the redox condition was changing in the Northeast region, Northwest region, and Central region. And we found that in this Northeast region, we had a small number of wells that changed, or small percentage that changed to more reducing, with the Northwest and Central region more changing, a higher percentage changing to more reducing conditions, and then the converse for the change into more oxidizing conditions, where in the Northeast, more wells were changing to more oxidizing conditions versus in the Northwest and Central region. But one of the findings that was actually quite a surprise to me was, even after a year, these so-called mixed conditions, and this means a condition where we have dissolved oxygen that's detectable, and we have high concentrations of manganese and or iron, all together, where we have measurable DO and high metal concentration in the water. So in the Northeast and the Northwest regions, about half of the wells were still in this mixed redox condition. And in the Central region, that was the most common condition, was this mixed redox condition. Not what I expected. I expected that there would be a much higher proportion of anoxic conditions versus the mixed conditions. So that was, you know, unexpected is interesting, right? So anyway, moving on to the next phase of the presentation of the temporal changes, I want to spend just a moment looking at this plot, because I'm going to present next a series of plots that look like this, and I want to orient everyone to what these plots are so that we can hopefully stay on the same page and have the same level of understanding of what we're looking at.
Could I ask you something before we move to this next phase?
Absolutely.
So hi, thanks, very interesting. I was wondering if we could go, presence of dissolved oxygen and iron puzzles me. You know the kinetics of iron oxidation. If there's any oxygen in the water, they're very rapid. You don't need microorganisms. The kinetics of manganese, it's something else. If you had told me co-occurrence of manganese and dissolved oxygen, I said, that's interesting. I'm wondering with this, maybe whether you're drawing water from two different portions of the aquifer, whether the pumping itself is adding oxygen. It's hard to imagine an aquifer with measurable dissolved iron and oxygen at the same time.
I agree with you. Those are excellent questions. All of the wells that we were sampling are domestic wells. So they are wells that have small flows in general. And they have short well screens because the putting in of a domestic well, the drilling is priced by the foot. And so the most common length of well screen is 4 feet. So just over a meter, right? These aren't public wells with, you know, massive screens or anything like that. So in terms of accessing different parts of the aquifer, probably less likely. I mean, certainly the flow is going to induce something. It's hard to tease out exactly what that could be. But I agree with you 100%. This was an unexpected finding for me. And if it had been a small percentage, it's like, okay, you know, something's going on, but that's not prominent. But the fact that we found these really common mixed redox conditions, and most of it was related to iron, it was much lesser related to manganese. That was a surprise, and it's actually something that Ben and I are in deep conversations about right now, to see what else we might be able to learn from what we found here in this study. So great questions. And yeah, I mean, it's part of why science is fun, right? Is we can still be surprised. All right, so we'll come back to this graphic here. Along the the y-axis, oops, sorry. Again, trouble with my mouse here. Along the y-axis, we have a measure of EH, or redox condition, as mentioned by our oxidation reduction potential. Oops, that's a typo. Oxidation reduction potential probe. It's just a scaled version of EH. So this is a measure of redox condition, with high numbers being more oxidizing, low numbers being more reducing. On the x-axis is the pH scale that I think all of us are familiar with. The circle size is illustrating relative arsenic concentration, which with the largest circles being about 100 micrograms per liter, and the smallest circles being about 2 micrograms per liter, and then scaled in between. And the circle color is discussing a general type of redox process that was calculated based on the measures that we had using a spreadsheet tool to look at dominant redox processes. So the red is an oxic condition as defined by high dissolved oxygen and low metals, the metals being iron and manganese. The blue is an oxic condition as specified by low dissolved oxygen and high metal concentration. The green is this mixed redox condition that I just mentioned, which means that we have both high dissolved oxygen and high metal concentration. And then the gray, I don't even know if there's one on this illustration, that's low dissolved oxygen and low metals. So that's the orientation to this: redox, pH, circle size, arsenic concentration, circle color, dominant redox process. All right, take a breath here just for a sec, and then move on to the context of our regional geochemistry. So in the Northeast region, and each of these next few figures are going to be round 1 results on the left, round 3 on the right. You can see that in round 1, the condition of both redox and pH is pretty spread out in this sort of a representation, and draws into a little bit smaller area by a year later, or by round 3. From round 1 to round 3, oxic becomes the most common condition, with the bedrock wells shifting to being more oxidizing and the glacial shifting to being more reducing. About half of the wells that were sampled in this region were bedrock and half glacial. All of the wells that have high arsenic at round 3 are bedrock wells. And our hypothesis for the mechanism is that arsenic is mobilized via sulfide oxidation, given that we're in this fairly oxic, fairly high pH regime here in this region. In the Northwest region, our final redox condition is split about equally between anoxic and mixed conditions, with about 34% of the wells shifting toward a more reducing condition over the year of the study. As you can see here in the round 3 diagram, we have a cluster of anoxic here at pH above about 7, and below pH of about 7, we have a mixed redox condition predominating for our high arsenic wells. And our interpretation here is that arsenic is being mobilized via sulfides and iron oxides from either oxidation or reduction based on the particular repository of the arsenic. And then finally, in the central region, this was the region that we had the biggest range of EH and pH in round 1 and the tightest clustering of EH and pH by round 3. But even here in round 3, we had about 70% of the measured redox condition being this mixed redox condition, with 45% of the wells shifting toward a more reducing condition. We also had this, this shift to a little bit higher pH, pH over 7. So our interpretation here is that arsenic is mobilized via reduction of manganese or iron oxides, and potentially also desorption because of the pH increase. So our takeaways from these two studies these two analyses of the results is that indeed the well testing or the well installation is disturbing the equilibrium, and that there's increasing arsenic concentration in the glacial wells over the course of a year, illustrating why testing wells at least twice, sooner and later, to look at that acute and the longer term exposure risks is a very useful public health idea. The other idea that we come away with is that measuring the easy to measure in the field parameters of pH and oxidation reduction potential can potentially give an indicator of the degree of disequilibrium that remains after a period of time, if a regional context can be applied for new wells that are being drilled or older wells that are being sampled. Where do they, how do they compare relative to other wells that are in the area? Another important takeaway is that if the geochemical change over time is toward more reducing, this can have really important implications for treatment technologies. So if treatment is installed and the geochemistry of the groundwater is going to change over time, that initial choice of treatment system may or may not be very effective as time goes on, or might require more frequent maintenance than what had been expected. And then finally, we only did this study for about a year, so we don't really know how long it takes to get to that new equilibrium, if there is such a thing. And then the other point is that well drilling isn't the only sort of disturbance that can cause a disequilibrium. Climate changes, land use changes, other sorts of contamination like hydrocarbon spills can also cause a change in geochemical conditions that can affect arsenic mobilization and arsenic in groundwater. Okay, so that wraps up these two studies, and I'm just going to give you the sneak peek at the one surprise, or the biggest surprise that we had coming from from the study. And that was a well that had a whopping over 1,500 micrograms per liter in that initial driller collected sample. This was a result that, I mean, is virtually unheard of in the upper Midwest and resulted in sort of an emergency meeting of everyone related to drinking water enforcement. And then I was called in as an expert related to arsenic specifically to try and understand what was happening. And one of the things that we ended up doing was enrolling this well into the study just to get a handle on what was happening at this particular well. And as you can see from this little graphical abstract, over the course of the study, that arsenic concentration did decrease to below the drinking water standard to 5 micrograms per liter. But it was still such a stunning result of pretty significant public health importance that it was something that I wanted to better understand what likely happened so that we could, you know, have some understanding about potential ways to mitigate in the future. And this paper is in press right now with the Journal of Hazardous Materials in a arsenic special issue. So again, hot off the presses. So because we had limited geochemistry that we measured and couldn't measure everything all the time over a period of time, we did some geochemical modeling to try and understand what happened in this well. Looking at the larger suite of geochemistry, looking at the total and aqueous arsenic, again, very high initially, still pretty high after 3 weeks, significantly lower after about 4 months, and then dropping off to pretty low, well below the drinking water standard another year after this round 2 sample was collected. The iron and sulfate, the iron increased and the sulfate decreased over time. The pH, we didn't have a measurement from drilling day, but the pH was still only about 3 during our round 1 sample 3 weeks after the well was drilled. And then increased to the circumneutral range over the remaining months of the study. And the redox condition was quite oxic initially, and then diminished to not quite anoxic, but a much lower dissolved oxygen reading and a much lower ORP reading over the course of the time. So we put together some hypotheses to test with geochemical modeling to see what may have been the trigger and cause of that very high arsenic concentration spike. The first mechanism that we considered was oxygen oxidizing arsenic-containing iron sulfides. The second was that the strong oxidizer chlorine, which is used as a disinfectant, oxidized the arsenic-containing sulfides. And finally, we looked at a combination process where the oxidation by chlorine of sulfides lowered the pH to dissolve and release arsenic-containing oxides. So those are the 3 primary mechanisms that we considered as possible for this high arsenic release that lasted such a short period of time. And through the geochemical modeling, this mechanism of the sulfides being oxidized by the chlorine, and then in turn reducing the pH and dissolving the iron oxides was the process that agreed the best with the measured geochemical conditions, where we had this steep increase in arsenic, aqueous arsenic, a decrease in sorbed arsenic, a very significant decrease in pH, and increase in iron. And so those together were were what led us to conclude that the hypothesis of the combination of sulfide dissolution and oxide dissolution led to that high arsenic spike. And then the final takeaway was replotting some of the geochemical data in the context of iron stability instead of arsenic. And so this is the same sort of a diagram that we were looking at before, where we have this EH or redox measure on the y-axis and the pH on the x-axis, but we have the stability fields for iron plotted in the background here, with the bubbles still being arsenic and concentration indicated by circle size. This is our study well, really high concentration, very low pH, very high redox condition. This is solid phase iron, aqueous phase iron, and then the equilibrium line between the solid and the aqueous phase. So this is the initial measurements of arsenic for all of the central region for that initial round one sample. And you can see that we've got this big spread of concentrations in the EH-pH diagram, but this really high concentration well is a pretty big outlier from all of the rest of the wells that were measured. If we look at how everything plots up in that round 3 sample, that year later sample, you can see that our study well is right in the mix with all of the rest of the wells for that central region. But one of the things that I thought was an important message also is that even here a year later, the common place for the arsenic to lay in the iron stability field is right at that equilibrium line between solid and aqueous iron. So small perturbations in pH or EH can still be triggers for arsenic release or sequestration, even in this, quote unquote, equilibrium condition a year later. And I think that is all I have. Always important to acknowledge both our funding from the state of Minnesota and the USGS and the National Science Foundation, and our samplers. These are health department staff members who spent the better part of 2 years out there collecting samples in support of this study. And then finally, the cooperation of the well owners and the well drillers. Study wouldn't have been possible without them. And with that, I would be happy to take questions that we have time for. Thanks.
Thank you. Thank you so much. Yes, let's take some questions. Please go ahead, Lex. People can just speak. Yeah.
All right. Thanks. Thanks again. That's a very interesting presentation. I have a question, or maybe a comment on this increase in arsenic over time. I've never installed a well in the US, several hundred probably in Bangladesh over the years. And one thing that is done in Bangladesh is that, or at least we try to encourage, is that the type of sand that is used to put around the filter is orange oxidized sand. And you could imagine that that would, temporarily act like an arsenic removal system, and that it would reach its capacity. How is that done in the US? Could what you are putting down the hole around the filter, could that maybe explain some of these changes over time?
That is a good question, and one that I hadn't really considered or thought about. That would be something to maybe think about, but it's not something that we considered as part of the study.
Mindy, can you see the chat? Because we have a couple of questions in the chat.
Let me see if I can figure out how to do that. I'm gonna stop sharing my screen first, if I can figure out how to do that. There we go. And then I'll have more room for the chat. There we go. Okay. Sure. So I'm going to read the question. Does your state license or healthcare facilities report drinking water resource exception data to your state Department of Health? Are symptoms and comorbidities included? I honestly don't understand what that question means, so sorry.
I think if I can translate myself,
Yes,
if I understand correctly, is if the state licensor, I believe if you need to report the findings of your drilling results to the Department of Health, to the state.
That's required. That's correct.
That's correct. And the second, when you do that, do you collect any information from the household members who live in that house?
No, nothing like that is collected. So this initial study that I was part of back in the late 90s, we did that. We had water sampling, and then we collected hair and urine samples analyzed for arsenic. But it was an effect biomarker study, so there wasn't any inclusion of health outcomes specifically. I think that's an obvious next step, but not something that is happening at this time, as far as I'm aware of.
Mm-hmm.
Certainly, it's not being reported with the water sample result.
Mm-hmm. And then there is a second question regarding if the chemistry was known to the policymakers or to the industry practitioners. So I understand it's from the results that you've done yourself, if that.
So all of the water well testing in Minnesota and the well drilling records are available online. They're just, I mean, there's a website that's called the Minnesota Well Index that you can zoom in, you can click on a well, you can see when it was drilled, you can see its construction, you can see any chemistry that have been reported. So all of that is publicly available information. And then the state also has done some summaries and presented data that they have in context. So there's an arsenic focused map, and there's a nitrate focused map, and some other focused slices and dices in addition to sort of this overarching presentation of the underlying data. So there's good, I think, remarkably good availability of the data.
Excellent. And Steve, you have a question, yes?
Yeah, it was getting to these mixed sites that you see, you know, even up to 12 months later. Are there, you've been working in the area for a while. Do you have any wells that aren't related to well installation, just going out and doing other studies where you still see this mixed redox setting with high iron and manganese and high DO? Or
that's a really good question, and I did not go back to some of the older data. There are some older data sets of, you know, visiting older wells and that sort of thing, like the study I was mentioning from the late 90s. I have all those data, and there is a good suite of geochemistry available. I haven't run the analysis on those results. It's actually a really great idea. Ben, let's do that.
There is some, you do have a paper that comes to mind where you show that there are a lot of arsenic wells that don't appear to have any iron in them, which is also sort of a little, you know, or at least depending on how you define iron reducing conditions, certainly. And those are not related to installation, at least in the way you present the data. But certainly it certainly is an interesting question. I have a question related though. So what you talk about with like sort of the idea that we can perturb sulfides and oxidize them. How much evidence do you have in your data sets or the information that you've aggregated over the years about nitrate and the incursion of nitrate into groundwater and how that could oxidize sulfides and be responsible for some of the higher arsenic values that you see?
Yeah, it's actually a really good question. In general, we have found that if we have high arsenic, we don't have detectable nitrate. And that's not to say that there wasn't nitrate at one time, but when we've done the measurement, there's no nitrate. And so I haven't thought a lot about whether nitrate might be a big part of the story. It could very well be in some of these shallower wells, especially as land use is changing in that northwest part of the state that used to be not as agricultural, and it's getting to be more agricultural, especially irrigated agricultural. And so there may be some things, happening right now that haven't been well studied yet. So that's a great question, and one I don't have an answer to right at the moment.
So Mindy, we need to finish soon, but there are two questions that I think quickly, if you can answer, will be useful. One is if you have any information on uranium, because arsenic and uranium might precipitate together and decrease arsenic concentration, and also as relationship with carbonates. That's one question. And the second is about the operation of the household pump and valves allow the reverse flow of chlorinated water back down the well during regular operations. So if you could cover quickly those two.
Sure. So there are limited data sets that have a lot of geochemistry, other elements like uranium, et cetera. And if you want to contact me afterward, I can help connect people to resources for additional groundwater geochemistry, because there are, that information does exist for a subset. It's not, tens of thousands of wells, but certainly hundreds of wells. And then the operation of the pumps, I don't know anything about that, so I can't answer that question. It's interesting, but I just don't know.
So thank you so much, Mindy.
You're welcome, and thank you for the invitation.
Wonderful. And then, so let's move. Stay, don't leave, don't go anywhere. Thank you so much.
I'm just going to shut off my camera. So thank you.